Hello, this lecture will review some basic concepts in number systems. The three number systems that we're going to concentrate in this course are going to be decimal, base 10, binary, base 2, and hex, base 16. In talking about a base R, we need to talk about the digits in that particular base. A digit in a base R range from 0 to R minus 1. So the digits in base 10 range from 0 to 9, while digits in binary or base 2 range from 0 to 1. But what about digits in base 16? The first 10 digits are obviously going to be 0 to 9. But after that, what are we going to do? The digit 10, we cannot use two separate symbols for that. We have to use one symbol. So what we're going to do is we're going to use letters for digits 10 and higher. So for digit 10, we're going to use the letter A. For digit 11, we'll use the letter B, and so forth. So this is going to be 10, 11, 12, 13, 14, and 15. When writing a number in a particular base, we're concerned about the value of that number. And how do we get the value? It's easy. We're going to take each digit, multiply it by a weight, and then sum those together. The weight of each digit is going to be a power of the base, and that power is determined by the position. So for example, this is obvious stuff. 953.78, the weight of this digit, the first one to the left of the decimal point, is going to have a weight of 10 to the 0. The next is going to have a weight of 10 to the first, which is going to be 10. The next is going to have a weight of 10 squared, which is going to be 100. Going to the right of the decimal point, we simply go down from 0. So this first one is going to be for 7, is going to be 1/10, which is going to be 10 to the negative 1. The weight of this digit right here, 8, is going to be 1/100th, which is 10 to the negative 2. We multiply that out and sum it, and we get the value of our number. So if we're converting from a number that is not base 10 to base 10, all we do is we simply multiply each one of these digits by its weight, sum them together, and we'll get that decimal equivalent. So for example, going from binary to decimal, all we need to do is start multiplying by the weights of the digits. This guy right here, that one, the first one to the left of this one, is going to have a weight of 2 to the 0, which is going to be 1. This one right here is going to have a weight of 2 to the first, the next one 2 squared, the next one 2 third, and so forth. Any digits to the right, we'll start at 2 to the negative 1 and work our way down. So that's going to be a half. That weight's going to be a half. This weight's going to be 0.25. We sum all those together and we get 11.75. So what we've done is we've just converted a binary number to decimal. Let's do the same thing for a hex. In this case, if we start with the leftmost digit, 15, and start working our way to the left, we'll have 15 times 16 to the 0, plus this digit 2 times 16 to the first, plus this digit 10 times 16 squared. We sum all that together and we get the decimal number 2607. In writing binary numbers in this class, we'll use this notation right here, a 0b in front of the number, in order to indicate that it's a binary number. For hex numbers, we'll use a 0x often to indicate that it's a hex number. Sometimes we'll leave these off if the context of the usage is obvious. Now that we've converted a number to from some base to decimal, let's go the opposite direction. Let's convert decimal to some base other than decimal. We're going to use a successive division algorithm. We're just going to take a number n that we want to convert to base R, and what we'll do is we'll successfully divide it by base R until we get a quotient of 0. The remainder at each step is going to be a digit in that particular base, and the digits that we're going to get are going to start with the least significant digit and proceed to the most significant digit. So let's start. We'll take 53 divided by our base 2. We'll get 26 and the remainder of 1. So this is going to be our first digit, and this digit is going to be our least significant digit, which is going to be our rightmost digit, and that's going to correspond to this digit right here in this number. So we'll now take that quotient 26, bring it over here, divide by 2, we'll get 13, a remainder of 0. That's our next digit, which is going to be that digit right there, and we'll keep proceeding. So now 13 over here, divide by 2 is 6, a remainder of 1, and proceed on until we get, finally, we're going to get a quotient of a quotient of 0 when we take 1, divide by 2, a quotient of 0, and our remainder is going to be 1, and this is going to end up being our most significant digit, which is going to be our leftmost digit. Once you get a number converted, you can always check your work by expanding that number out and multiplying by the weights, which we do here, and we end up getting back our original number of 53. Our previous example converted 53 to binary. Let's take the same number 53, but this time let's convert it to hex or base 16. So we'll take 53 divided by our base, which is 16, we'll get 3. What's our remainder? Well, 3 times 16 is 48. We'll subtract that from 53 and we'll get 5 as our remainder, and that's going to be our first digit, which is going to end up being our least significant digit, which is our rightmost digit. We'll take our quotient, bring it over here, divide by 16, that's going to be 0 with a remainder of 3. When we get a quotient of 0, we're finished. So this is our last digit, which happens to be our leftmost digit or most significant digit. So a decimal 53 is going to be a hex 35. We can check our work by multiplying out by our powers like we do here. So 3 times 16 to the 1 plus 5 times 16 to the 0, we get 48 plus 5 is 53. So we've done the correct conversion. Let's discuss some shorthand methods from going from hex to binary and binary to hex. Going from hex to binary is trivial. We will take each hex digit and expand it out to its 4-bit equivalent. This A is a 10, and a 10 in binary is 1010. This has a weight of 8, has a weight of 2, so 8 plus 2 is 10. This digit right here, 2, its value is going to be 0010. That's a binary 2, and this 15F is going to be all ones, as 8 plus 4 plus 2 plus 1 is 15. Similarly, we can convert this to binary. 3 in binary 0011, 4 in binary 0100, and 5 in binary 0101. So converting from hex to binary is easy. Just take each hex digit and write its binary equivalent. Going from binary to hex is simply the opposite. We're going to end up grouping the binary digits together in groups of 4, and we'll do it starting with the leftmost group of 4 digits. I'm sorry, the rightmost group of 4 digits and moving towards the left. So this is the rightmost group of 4 digits of 0001. That's going to be our first hex digit, which is going to end up being a 1. Moving to the next group of 4 digits, we only have 3 digits actually, 101. So we need to pad with 0, and we'll get this right here, 0101. That will be our next hex digit right there, which is going to be a 51. So this binary number in hex is simply going to be a hex 51. This slide helps you remember hex digit to binary digit correspondence. You simply start writing hex digits in counting order, 0, 1, 2 up to 15, and do the same thing for binary, 0, 1, 2, 3 all the way up to 15. You can see the correspondence. This also reminds you the decimal correspondence. This is going to be 10, this will be 11, this will be 15. It might be a good idea for you at the beginning of a test to write this table down in the corner of a test somewhere to help you when you're doing your hex to binary and binary to hex conversion, as well as reminding you what the correspondence is between the hex digit and their decimal representation. So let's start talking about some simple arithmetic operations on our 3 favorite bases, decimal, binary, and hex. Let's start with addition. So here's simple addition. We're going to add 34 plus 17, and we'll get 51. So now you can do this in your head very fast, but what is actually happening? Let's parse this out. We're going to take 4 and add that to 7. When we do that, we're going to get 11. We can't write 11 down, so instead what we're going to do is we're going to subtract the base. We'll subtract 10, and we're going to be left with a digit of 1, and that's what's going to go right there, and we're going to get a carry of 1 over to this column here. So this next digit right here is going to be 1 plus 3 plus 1 will end up being 5. The exact same rules that are in decimal apply to any other base such as binary. Let's do a couple of binary additions over here. We're not going to add this whole number. We'll just do a couple. So here we're going to take this 1 and add it to this 1. Well, 1 plus 1 is going to be 2. We can't write 2 down because that exceeds our base. So instead we'll subtract our base and we'll get 0. So 0 is what we're going to be left right there. And we're going to have a carry of 1 into this column. So now we have 1 plus 1 again is going to be 2. So we're going to have a 0, another carry of 1 over here. 1 plus 0 plus 0 is going to be a 1, and so forth. So that's binary addition. It works exactly the same way as decimal addition, except we're using a base of 2 instead of a base 10. So now we did binary addition. Let's try hex addition. So we're going to add the hex number 3a plus 2a. So let's add this one digit at a time. A plus 8. What is that? Actually, it's going to be 10 plus 8 is 18. 18 exceeds our base, which is 16, so we're going to subtract our base, and we're going to be left with the value 2, and that's what's going to be left right there for that digit, and we'll have a carry here of 1. Now we have 1 plus 3 plus 2. 1 plus 3 is 4, plus 2 is 6, and we'll be left with our last digit of 6. So our 3a plus 2a is going to be a hex 62. You can always convert this to decimal and check if you wish to do that. Now that we've done addition, let's do subtraction. So we'll do a simple subtraction of 900 minus 1, and the obvious answer is 899. In doing this, what is actually going on? Let's expand this out. We have 900 minus 1. We cannot subtract 1 from 0. We've got to do a borrow. Where we borrow, we're going to look for a non-zero digit. The first non-digit was going to be 9, and we're going to borrow a 1 from that. It's going to leave an 8, but borrowing a 1 is actually, what we're actually doing is actually borrowing 10 in this column, so this digit right here becomes 10. We still haven't borrowed into here yet, so now we've got to borrow from this column into here. So we'll borrow 1 from that, which is going to leave that as 9, and that's going to make borrowing 1 here makes that a 10. So 10 minus 1 is going to be a 9. This is a 0. 0 from 9 is 9, and then 0 from 8 is 8. The shorthand rule is that when we're borrowing across multiple 0 columns, we just leave the columns of whatever the base is minus 1. In this case, it would be 10 minus 1 would be 9. And that's what happened here. We can do the same thing in forming binary. And doing binary subtraction, we want to do 100 minus 001. Let's see how this works. Let's expand this out. We're going to have 100 minus 1. So we need to borrow. So we're going to borrow 1 from here. That's going to leave that 0. That's actually going to put a 2 there. We still need to borrow from that column. So we're going to borrow 1 there. That's going to be a 1. That's going to leave that's going to borrow the base. It's going to be 2 here. 1 from 2 is going to be 1. This is 0. 0 from 1 is going to be 1, and that's going to be 0. So we get a final answer of 011. In order to check this, we know that this value right here, 100, is actually a 4. This is actually a 1. 4 minus 1 is 3, and this value right here is a 3. So now that we've done binary subtraction, let's do hex subtraction. So we'll do hex 34 minus 27. So let's write this out and see what is actually going to happen. So we want to subtract 7 from 4, which we can't do because 7 is less than 4. So we can either borrow from this column right there, borrow 1 there, it's going to leave that as a 2. Borrowing a 1 in base 16 means we're actually adding 16 to this column. So 16 plus 4 is going to be 20. If we should say 20 minus 7, that's actually going to be 13. But we know that 13 is actually a D. So now we have 2 from 2 is going to be a 0. So the final answer is going to be 0D. We could actually check this in decimal by converting 34 to decimal, which is 52, converting 27 to decimal, which is 39, subtracting the 2, and we get 13, and indeed we did get the correct answer. So let's talk about the concept of fixed precision. When I write a number on a piece of paper, I can use as many digits as I wish, as I did there with this ridiculously large number. However, if I actually build a computing system out of hardware, I typically have internal registers that are limited to a fixed number of bits. And that fixed number of bits is typically some multiple of 2, such as 64 bits or 32, 16, or 8. Or I can also declare variables in a programming language, and I declare a variable in a programming language. Those variables are typically limited to a fixed number of bits as well. That's called the precision of the number. It turns out that high-end microprocessor computing systems will use either 64 or 32-bit precision for their integers, while low-end will use 16 or 8-bit. The processor that we use in our class, its internal registers are 16-bit registers, so we refer to as a 16-bit processor. When using a fixed number of bits to represent a number, that means that the number will be limited to a to a particular number range, and that number range will depend on if it's an unsigned integer or signed integers. We're going to initially just discuss unsigned integers, and we'll typically either use 8 bits or 16 bits for our number size. For 8 bits, the range of unsigned integers ranges from 0 to 2 to the 8th minus 1, or 0 to 255. For 16 bits, it's 0 to 2 to the 16th minus 1, or 0 to 65, 535. In general, for an n-bit number, an unsigned number can range from 0 to 2 to the n minus 1. Given that we have a limited range of numbers, then when we do an operation on a number, we can overflow the range. For example, when I add or subtract two numbers together, if I get a result that is outside of the range of the allowable numbers for precision, then I get the wrong answer. In that case, I will get overflow if I produce a number that's too large for a particular number range. Let's assume that I have 8-bit precision. That is, the registers that I'm using to hold my answers can only store 8 bits. And let's add a couple of numbers. Let's add 255 plus 1, and the correct answer should be 256. So I'm going to write this as hex numbers. 255 is actually a 0xFF. A 1 is a 1. If I add these two numbers, let's see what I get. 1 plus 15 is going to be 16. So that means I'm going to have to subtract 16 and leave behind a 0 here. So this is going to be a 0. I'm going to have a carry out of 1 here. A carry out of 1 plus 15 is going to be, again, 16. So I'll have to leave a 0 behind and have a carry out of the most significant digit. In my 8-bit register that's holding the result, I get a value of 0. That is, if I'm just looking at these 8-bit result here, the answer is wrong. And that's because I've overflowed the range. Remember that the maximum number that I can represent in 8 bits is 255, but I tried to produce a result of 256, which simply will not fit. Whenever I get a carry out of the most significant digit, that means that the remaining bits by themselves are incorrect, and that unsigned overflow has occurred. So a carry out of the most significant digit means that unsigned overflow has occurred in my operation. Up to this time, we've been viewing binary digit strings as simply representing some number, but we can also view them as representing some abstract value, such as a color. For example, if I had 3 bits, 3 bits can represent 8 things. I could use each binary code of those 3 bits to represent a color. For example, 000 could represent black, 001 could represent red, and so forth. We often use binary digit strings in this manner, in which we assign them as codes for representing some abstract quantity. So one thing that we need to store on a computer is text. And how to represent text? Well, one way to represent text is by a code, a 7-bit code known as the ASCII code. That stands for American Standard Code for Information Interchange. Even though it's only a 7-bit code, we typically write as an 8-bit value, with the most significant being a 0. A couple of examples of ASCII code are the following. A capital A is a 0x41 in hex, and an ampersand symbol is a 0x26. With 7 bits, I can represent 128 different values, and that's plenty to represent capital and lowercase capital and lowercase letters, as well as digits, as well as punctuation marks and other special symbols. This slide shows a complete table for the ASCII code. The columns here represent the most significant hex digit of the code, while these rows represent the least significant hex digit. If I wanted to find the ASCII code for a capital B, I would look for B, and this would be the most significant hex digit of 4. The least significant hex digit would be a 2, so this is going to be a 0x42. These columns show some of the special symbols and digits that are represented in the ASCII code, while this has some non-printable characters that are represented. CR, for example, stands for carriage return, while LF stands for a line feed. In this class, when representing characters, we will always use the ASCII code instead of a larger code such as Unicode, which is used by web browsers. So this concludes the lecture on number systems. So what should you practice in order to solidify this information? You should definitely practice hex to decimal and decimal to hex conversions, as well as hex to binary and binary to hex conversions, and particularly practice hex addition and subtraction skills. Just make up problems and do them, and then use the Windows calculator to check your work.